Hello. Quick video on creating summary scales. Um, Sorry this is a little late. Thought I'd get to it earlier this week, and that just did not happen. So these four libraries are the ones that or these four packages are going to be the ones that we need to use in this video. So go ahead and run those lines there, and then import the data set that we're currently on. And we're going to need to scale some of our variables. So let's run this function so that it's in our environment. Okay, so I am creating the summary scale here, and it's going to be, I think it's like, what do I end up making it be called? I guess party ID scale is what I end up calling it. So I have these three variables that I think are going to go well together to create this scale. First thing we have to do is make sure that they all have the same range, which is why we needed to run the scale function there. So I'm taking the Republican variable and the Republican Party feeling thermometer and the Democratic Party feeling thermometer. And I'm going to scale these so that they're all on this negative 0.5 to positive 0.5 scale. And the Republican, this is my party ID variable. So remember, Republican was at the top end, so the high end of the scale. The Republican Party feeling thermometer is also going to have the large end of the scale be for feeling warmly about Republicans. So we can think of those two as going in the same direction. So they should be positively correlated. However, the Democratic Party feeling thermometer is going to be the opposite. It's going to have a negative relationship. So what we actually want to do with that one, in order to get it in a format that would actually work in the summary scale, we want to reverse it. So to do that, we just simply take the variable as it is and subtract it from 100. This essentially flips it, and then that is then wrapped in this scale function. So the first two are just very straightforward. You're just creating a scaled version of each of these already existing variables. And this one, we flip it and then scale the flipped version. So here I just have this the st function, which gives us our descriptives, and then the three variables that I just created plugged into that, so we can take a look at it and just make sure that everything makes sense, that yes, indeed it worked. We have a range, all three are on the same range from negative 0.5 to positive 0.5. Next, we want to take a look at the correlation matrix. So if we actually feed the core function that we've already used in previous assignments a subset of our data that includes just the three variables we're using in our scale, then we get this matrix of correlation coefficients. So rather than like when we did this before, it would just spit out the single correlation for the two variables that we input. Since we're now inputting multiple variables, it's going to give us a matrix similar to what you saw in Rick's slides the other day. Except for, I believe in his slides, it didn't have this top part, it just had the bottom part. You notice that, this is the same as this. This one is the same as this one, and this one is the same as this one. So it's just mirrored, essentially. Yeah, so what we want to make sure is that everything is positive here. If we had something that was negative, that would indicate that we cannot scale these or make a summary scale of these variables. But not only are these all positive, they're all pretty high as well. To know how high or how strong these are, or how well these variables go together, we have this function Cronbach alpha that comes out of the desk tools package that we've used before, and that we open that package at the beginning of the script. If we run this, it gives us that Cronbach alpha, and that's super high for Cronbach alpha. I can't remember what Rick said the threshold was, but I feel like it's only like 0.4 or 0.5. It's really actually not that high. So we're in good shape. That means all of these variables can go together and create this summary scale. So to do that, we're going to use the row means function in the library sjmisc. And it takes the form of row means, and then inside the parentheses, x is a data frame of the variable used to compute the scale. N equals 0.5 here indicates that the data for at least half the values must be non-missing. And append equals false, this final argument here, returns only the mean rather than a data frame of the input variables and the mean. So whatever our new variable is, whatever we're going to call it, that's what we're creating this new variable that I call party ID scale. And then of course the assignment operator, and then we put the function in here and we feed it, the data frame, and then the three variables that we're talking about here. This argument to make sure, and this Rick was talking about in class, pairwise comparison and listwise deletion and all of that. So this retains, rather than dropping out and giving us an NA for any, so if any of these was an NA, I think listwise deletion is the term for, then it would just throw an NA when you create this index. But this n equals 0.5 says that as long as two of them are here, to go ahead and average those, even without this other one. So if this was an NA, but this value was here and this value was here for a particular observation, then it would retain it. But if this was an A and this one was an A and only this one had a value, then it's going to throw an NA in our new variable. I hope that I didn't just make that super confusing, because I feel like I kind of jumbled that up. But if you have questions, email me. So I'm going to go ahead and run this. Now, if you look at the data, oh shit. Yeah. So it has this like row means label on here. And if you actually look at this in your data set and go all the way till the end here, you see, rather than being called just PID scale, it's PID scale $row means. That's because what this function actually creates is a list, not just a variable. So it creates a list that has not just the row means, but it actually also has other things in there too when it creates it. So if you were to put append equals true here, kind of show you what I'm talking about. And then it's going to give you like all of those values. So the value for this variable that we use and this variable that we use and this variable that was used, and then the summary and the summary scale. But with append equals false, all we wind up is just this one column. I'm going to skip this because that's not really that relevant. So let me fix this by running this function. So we're back to just having the single thing here. And to fix this, to get rid of this, because it'll cause problems for you later on, if you leave it like that, you just force it into a normal variable by just repeating this name that we just gave it, and then feeding it the actual how it exists in the data frame right now. And then this just kind of like coerces it into just a regular variable. So if you run that and then you run this, you see now that this is a vector. And if you run this, actually look at it in the data set again and go all the way to the end. Now you see it just does say PID scale, not PID scale $rho means. Okay, so I don't know, I feel kind of like I might have made that more confusing than if you just would have gone through the script yourself. So if I did super confuse you, I'm sorry. Like I said, come to office hours or shoot me an email. But hopefully this gets you through the next assignment. I mean, really just the important part is make sure they're all scaled with the same range. Make sure that they are all positively correlated, that they have an acceptably high Cronbach alpha. Then use this function to create the new variable, but then run a function similar, or run another line of code similar to this with whatever you name your variable plopped in here, but with the $rho means at the end, so that you get rid of that list and you coerce it back into a normal variable. Okay, thanks, bye.